Okay, so we're going to start module 5, which is alkanes and cycloalkanes. So we're going to look at alkanes and cycloalkanes. And you remember that alkanes have the generic formula CN, H2N plus 2. And then cycloalkanes, depending on whether they've got one ring or two or more, will have CN, H2N for a monocyclic, CN, H2N minus 2 for a bicyclic, CN, H2N minus 4 for a tricyclic. Because remember, every time you make a ring corresponds to one HDI, one hydrogen efficiency index, which means you're missing two H's. So if I've got a monocyclic, then I'll miss two H's. So I'll be CN, H2N, H2N. If I've got two rings, then I'm missing four H's. So I'll be CN, H2N minus 2, and so on. So it'll be CN, H2N for monocyclic, and then CN, H2N minus 2 for a bicyclic, and so on. So what we'll do today, because there's a lot to consider under alkanes, and so what we'll do today is talk a little bit about the properties of alkanes and cycloalkanes. We'll talk about how they're prepared, and we'll talk a little bit about their reactions. And then in the next lecture, we'll look at their structures, in particular the stereochemistry. And then if we don't get to it today, which I don't think we will, we'll also look at the features of the sizes of the rings. So we look at 3-membered rings, 4-membered rings, 5-membered rings, and 6-membered rings. So you remember that if I look at CnH2n plus 2, then as the value of n changes, right? As n is 1, then my CnH2n plus 2 becomes CH4, and that name is methane. And we covered this several lectures ago, so I won't spend much time on this. When n is 2, that becomes C2H6, and that is ethane, right? Which has that's a CH3, CH3. And when n is 3, then we've got C3H8, and then we're into propane, which I can draw like that. And then once you get into C4s and beyond, you start getting isomers. You start getting constitutional isomers of the alkanes. So we've covered this before. I'm not going to get into more detail. I would remind you, you're responsible for the prefixes, the meth, the eth, the prop, for C1 to C12. Okay, we've talked about that before. You can go over one of the previous lectures and on nomenclature, and you can cover that. What we're going to do is talk about the properties of alkanes and cycloalkanes. And really, when we talk about alkanes, even though cycloalkanes generally would be missing either 2 H's or 4 H's or 6 H's or more, depending upon whether they're mono, di, tri, cyclic, tetracyclic. The chemistry of alkanes and cycloalkanes are virtually identical. This is not surprising because the structures are very much the same. These are compounds that will have only carbon-carbon single bonds and carbon-hydrogen bonds. And since the type of bond dictates both the physical and chemical properties, we talked about this in functional groups earlier, then we'd expect alkanes and cycloalkanes to behave in very much the same way. In fact, one can even make the argument that cycloalkanes are sort of a subset of alkanes. You can sort of make that argument if you you kind of wave your hand a little bit. So whatever I say for alkanes pretty much speaks to cycloalkanes as well, right? Because their physical properties and their chemical properties, their physico-chemical properties, are dictated by their structures. And all of these compounds will have carbon-carbon single bonds only, no double or triple, and carbon-hydrogen bonds only. So if you only have CC single bond and CH single bonds, your chemistry is going to be pretty much identical. So what are the properties we expect for alkanes? And let's talk now about physical properties. Okay? Well, the physical properties, if you remember, will be dominated by van der Waals interactions. Because alkanes, and cycloalkanes, are non-polar compounds. They've only got carbon-carbon single bonds, which are non-polar, because carbon is attached to carbon, so there's no difference in electronegativity, the bonds are non-polar. And then as far as we're concerned, particularly in this course, the CH bonds themselves are non-polar. That the electronegativity of H and carbon are so similar, the bonds are functionally non-polar. Now, that's not entirely true, but for the major considerations of this course, we'll take that as being, practically true. So alkanes are, so this is dominated by van der Waals bonds, bonding. So what does that mean? It means then that alkanes are going to have very low boiling, well, let's start with melting points, very low melting points. They will have very low boiling points. They will have very low aqueous solubility. They will have high solubilities in non-polar solvents. They will have low viscosities, low surface tension, and so on. Okay? So let's just talk about those for a little while. Again, this will be recap because we've covered this in great detail when we looked at intermolecular forces. So you recall that the factors affecting physical properties are the intermolecular force, both the nature and the number. The other factor was the mass, and the third, which was sort of a fine-tune, was the shape. So, since these compounds are non-polar, again, carbon-carbon bonds are non-polar, and then the CH bonds are non-polar. Since these compounds are non-polar, then the bonds between them are van der Waals bonds. Van der Waals bonds, if you remember, are the weakest of the intermolecular forces. So what that means then is that if I'm looking at melting a compound that is van der Waals bonded, right? If I'm looking at melting that compound, so now I'm disrupting the lattice, if you will, well, the bonds between these particles, so X's are my particles, the bonds between them are pathetically weak, which means they're very easily disrupted, and I do not have to pay a lot of thermal energy to break them. Again, the melting point is a measure, it's a proxy of the amount of thermal energy I need to melt the compound, to break those intermolecular forces. And if the bonds are very weak, then I don't have to pay a lot of energy. And therefore the melting points are going to be low. Okay? Further, I can make the same argument, in fact, with the boiling point. Right? So when I'm boiling a sample, what I'm doing is I am physically lifting molecule by molecule of the liquid from the liquid phase into the vapor phase. So what do I have to overcome? Well, I've got to overcome the bonds between the molecule and its neighbors. And if those bonds are pathetically weak because they're van der Waals, well, I don't have to pay a lot of energy to break them. They're easy to overcome. And therefore, if I need only a small amount of energy, then the boiling point is going to be low. Because again, the boiling point, like the melting point, is a measure of how much thermal energy I need to boil the compound. So I would expect compounds that are van der Waals bonded to have very low phase transition temperatures, very low melting points, very low boiling points. Now, that can be mediated by how big the compound is. So for example, while methane, ethane, propane are gases at room temperature, butane is a very volatile liquid. You're actually going to keep it under pressure. But pentane is a liquid, okay? Which means the melting point of pentane is modestly high, because it is a liquid at room temperature. So, right, so it's a liquid at room temperature. So in other words, we don't have solid pentane at room temperature. And then as we go from pentane to hexane and blah, 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 all the way down, by the time you get to about C40, the alkanes start turning solid. So as you make the compound heavier and heavier and heavier, well, more correctly, bigger and bigger and bigger, two things happen. As they get bigger, if you remember, the mass goes up, that's by getting bigger, which means the compounds get heavier, so it requires more thermal energy to move the particles, and fundamentally, phase transitions involve movement. So when I melt the substance, I'm increasing the mobility of the particles from just vibrating up and down, left and right, forward and back, to actually swimming through the liquid. I'm increasing the mobility. Well, the heavier I am, the more difficult I am to move. And I've got to pay more thermal energy to move me, therefore a higher melting point. The heavier I am, the more difficult it is to lift me from the liquid state and toss me into the vapor state. Right? Because I'm now working against the force of gravity. And therefore the boiling point is going to go up because the amount of thermal energy I need to lift the particle goes up. So it can be mediated by the mass of the compound. And of course, as you get more massive, what also happens is, and this also leads into the shape, is that there's a larger surface area for interaction. So you have more van der Waals interaction between the molecules. And again, shape plays a role. And we talked about this as well. If I have a long stringy isomer, and the classic case is to look at some of the pentanes. So if I look at the pentanes, so 1, 2, 3, 4, 5 carbons, this is what you might call N-pentane, versus the 2,3 dimethyl version. This will have a higher boiling point than that one, because it's longer and stringier, and therefore the interactions between the molecule are larger, or more, whereas the interaction between that molecule, which is essentially spherical, and another, that interaction is much less. So I would expect this one to have a higher boiling point than that, but since these are compact, they pack better, and therefore their lattices are more stable. So I've got to put in more energy to melt them so their melting points are high. And we talked about this before. Long stringy molecules, all things being equal, have elevated boiling points but depressed melting points. Compact, spherical molecules tend to have elevated melting points but depressed boiling points. So again, I'd expect alkanes to have very low melting points, very low boiling points. They will have low aqueous solubilities because the bonds between the alkane and the alkane, the solute, are van der Waals. The bonds between water and water, the solvent, are hydrogen bonds. The bonds between the alkane and water in the potential solution are van der Waals. So while the alkane has no problem going into water, water refuses that trade because the water molecules will be sacrificing strong, stabilizing hydrogen bonds for weaker van der Waals bonds. So the water lattice refuses to open up to admit the alkane. and therefore alkanes don't dissolve in water. Again, we talked about this in great detail before. If it's a little cloudy, I encourage you to go back to the lectures on intermolecular forces where we discuss this in great detail. But they will have high solubilities in non-polar solvents because you have van der Waals bonds between the alkane molecules, van der Waals bonds in the solvent, and so you end up with van der Waals bonds in the solution. So it's a fair trade, solute for solvent, and therefore they will dissolve rather readily in non-polar solvents. They will have very low viscosities, very low surface tensions, and of course they will. Right? Viscosity is resistance to flow. And again we talked about this in the lectures, if I take my test tube with my alkane in it, and I've got layers of alkane molecules in the test tube, the layers will slip by each other very easily because the bonds between one layer of the alkane liquid and the other, the bonds between these are very, very weak, right? Because they're van der Waals. So I can have, when I tip my container, the one layer will slide past the other very easily, and so the viscosity, the resistance to flow is very low. They'll have very low surface tensions. Because if this is the surface, for example, let's say this is the surface of my liquid, that's the surface of my liquid, well then if an object would impact the liquid, the bonds between the particles on the liquid are very, very weak. Right? That's in all two dimensions. The bonds between the particles are very weak, and so the particles will slide away from the object, from the force impacting, the force of the object generates on the surface. And therefore, because those bonds are weak, the particles will move as a result of the force, and therefore the surface of the liquid will break. So the molecules are weakly bound to the neighbors, and therefore they scatter very easily. The surface tension is low. So I can explain all of the physical properties of alkanes based upon the fact that alkanes are nonpolar. If they're nonpolar, the only interaction of which they are capable is van der Waals interaction. And that says everything. That means low phase transition temperatures, melting point, boiling point, low aqueous solubility, high solubility in non-polar solvents, low viscosity, low surface tension, etc., etc., etc. So we can talk then about the properties of alkanes and cycloalkanes based upon this model. And we can interpret that very nicely based upon the intermolecular forces. I will say that if you look, obviously, and this is a typical type of question, if you were to look at alkanes or cycloalkanes, haloalkanes and alcohols of similar masses, then what you'd expect is alcohols to have the highest melting point, boiling point, viscosity, aqueous solubility, then haloalkanes, and then alkanes at the bottom, right? And that's a consequence of the type of intermolecular forces. Alcohols, hydrogen bonding, that's the king or queen. Haloalkanes are dipole-dipole bonded, so those forces are strong, not as strong as hydrogen bonds. And then at the very bottom, they're van der Waals forces. So if I looked at a series of alkanes, haloalkanes, and alcohols of similar masses, then there's a gradual progression, right? So alcohols, let's say haloalkanes, and then alkanes way at the bottom. So if their masses were similar, these would have highest melting point, highest boiling point, highest aqueous solubility, lowest solubility in non-polar solvents, highest viscosity, highest surface tension, and then we go down that sequence. Consequence of hydrogen bonding between the molecules, dipole-dipole bonding between the molecules, van der Waals bonding, alkanes, van der Waals bonding between the molecules. And again, we've covered this in greater detail in previous lectures, so I'd encourage you to go back and look at those. Alright, so those are the physical properties of alkanes. let's talk a little bit about the preparation of alkanes. How do we make alkanes? And this part of it is going to dictate or dominate the rest of this lecture. So we can make alkanes in a number of ways, and I'm not going to. It's not a very common series of reactions nowadays to make alkanes, in the sense that alkanes tend to be readily available. Alkanes are what make up a natural gas. Natural gas is methane. Alkanes are what tend to be found in oil and so on. And so there's a fairly ready source of alkanes, although it is still at times necessary to make them by a series of processes. So we will introduce some methods of making alkanes today. I will say this is not by any means an exhaustive list, because there are quite a few that you will meet in second organic. But this is just meant to be an introduction to preparation of alkanes. So we looked at physical properties of alkanes. We're going to look now at preparation of alkanes. And again, when I say alkanes, I'm also tongue-in-cheek saying cycloalkanes. Well, there are several ways in which you can make alkanes. So I'll say one is by hydrogenation. And then two is from haloalkanes. And then I'll say three is by reduction of carbonyl compounds. So those are my very broad classes for now. There are quite a few others that we're not going to get into in Organic 1. Let's talk about hydrogenation. Now, if you remember when we talked in one of the previous lectures about the classes of organic reactions, we said that when we use the term, the suffix ation, ation means the addition of. And the term that precedes ation tells me what we're adding. So hydrogenation, right? Hydrogenation means the addition of hydrogen. Now, I've also pointed out that because there are two atoms in a double bond or a triple bond, I can't add something to one of the atoms and not add something to the second. Okay? So if I have, for example, a carbonyl compound, or I have an alkene, if I were to add hydrogen gas to them, and you will have to have some sort of a catalyst or whatever, or something, and there are ways of doing that. Well, what's going to happen is I'll end up with HOH. So I must perturb both atoms in the multiple bond. In a similar fashion, if I'm going to add this to an alkene, then what I would end up getting is that compound, which is an alkene. We're actually going to do these today. So what we're going to look at then is how we convert, how we do hydrogenations into alkanes. Now, obviously, if I do a hydrogenation of a carbonyl compound, a hydrogenation, I'll end up with an alcohol. That's not my target. So we're going to actually end up doing just the bottom reaction. So we can hydrogenate either an alkene into an alkene, or I can hydrogenate an alkyne into an alkene. But you can clearly tell in this case what I would have to do is add two equivalents of hydrogen gas. So for example, for every 1 mole of this, I would need 1 mole of H2. Because I'm only destroying 1 pi bond. But for every mole of this, I'll need 2 moles of hydrogen gas, right? Because I'm destroying 2 pi bonds in this process. So I need 2 equivalents of hydrogen gas for this one, right? This is 2 equivalents of H2. And this is just 1 equivalent of H2. The same number of moles, whereas this one would need twice the number of moles. So let's describe how this happens. Well, an alkene, if you remember, the carbons are sp2 hydrogens. So the alkene is actually a flat compound. It's trigonal planar. Well, the alkene is flat. It's trigonal planar, the carbons, it's trigonal planar about the carbons. Right? So it's a flat triangle about each of the carbons. The typical way, and there are several ways of doing this, but the one we're going to focus on is hydrogenation using a catalyst. And we're going to use a catalyst that is not in the same phase as the alkene. So typically the catalyst will be some sort of a metal catalyst. So as far as we're going to do this, it's going to be, well, I could leave that. As far as we're going to do this, it's going to be hydrogen gas, and it could be, we can use nickel as a catalyst. We could use palladium as a catalyst. We can use platinum as a catalyst. Very often, these catalysts are embedded on charcoal. So, palladium and platinum are much better than nickel. So the idea is both palladium and especially platinum are very expensive. And so what you do is you want to disseminate the metal, especially the expensive ones, over a broad, powdered, inert surface. So you use charcoal. Right? And charcoal has a wonderful capacity to adsorb, in other words, just a surface interaction, not absorb in the bulk, but just to adsorb anything on it. So what you do is you mix up the platinum or the palladium on charcoal, and you use that as your catalyst and support system. Some people use asbestos. Not all asbestos is bad. So I can either use what's called platinized asbestos, or I can use palladium or nickel or platinum on charcoal. The charcoal is inert. Its job is just to have a broad, large surface area. So how does this work? Well, the way it works, and I'm just going to go ahead and take this bit off, or I can go here. The way this works, and I'll start with the alkene, is that we're going to use some metal, right? So let's say I'm using some metal M. And this represents the metal surface. So the metal is exposed to hydrogen gas. Sorry, this is. My throat gets really dry when I'm talking for a long time. So the metal, I'm going to expose it to hydrogen gas. And the hydrogen gas gets adsorbed onto the metal. Of course, the metal itself is absorbed on the charcoal or asbestos. So what I end up getting is a complex in which the hydrogen molecule is bound to the metal surface, something like that. Now let me explain what's happening. The metal we're using is, as you can tell, a transition metal. And transition metals have low-lying, in other words, low energy, vacant orbitals, into which the electrons in the HH bond can be donated. So I'm going to use the binding power of these two electrons to now zip together metal, H, metal. Okay? So the hydrogen is bound to the metal surface. Of course, so M means the metal atoms here, right? All across the surface. So these H's aren't bound to the same metal atom necessarily, like they usually are. So I'm using these two electrons, which by right should only hold together two atoms in a typical bond. That's a typical Lewis bond. Two atoms, two electrons. I'm using those two electrons to hold together four atoms. Metal, H, metal. Well, what that means is two things. One, those bonds are very weak, which is why I drew them as dotted lines. Right? And we've used this trick before. When we were dealing with resonance, some bonds would be full lines, others would be dotted lines. And a dotted line indicates it's a partial bond. We're not going to quantitate whether it's a half or a third or a quarter bond, but it's a partial bond. That indicates it's weaker. So what I've done is I have adsorbed. To adsorb means to desorb or to have an interaction that is just on the surface. Right? That's adsorption, which is very different from absorption. To absorb with a B means to incorporate in a bulk. So I might, for example, say something silly like if I put oil in water, the oil floats on the surface, and that's kind of a surface thing. That's kind of an adsorb. But if I put vodka in water, the vodka is dispersed to the entire matrix of the water. That's sort of an absorption. So when I take a sponge and I put the sponge in water, the sponge absorbs water. That's a bulk thing, right? It's distributed through the entire matrix. So what we're looking at here is adsorption. But the net effect is I have taken one of the strongest bonds in chemistry, right? Because these are the two smallest atoms that bond. So we know small atoms make short bonds are strong bonds. I have taken one of the strongest bonds in chemistry, and I have made it really weak. Because there aren't two electrons now between those H's. Those two electrons, instead of zipping together two atoms, as per normal, are zipping together four. So they're spread more. There's less of electron density between these two H's.